Okay, so today is a set of notes on the Pythagorean theorem and what are called special right triangles. So the Pythagorean theorem you have seen is that if I have a right triangle, right triangle, and I call this A and this B and this C, then a squared plus b squared must equal c squared. Okay, so this is not a shocker. We've seen this before. We're going to look at a quick way to prove this that actually comes from just a little bit of algebra. Okay, so an easy way to prove this is to actually build a square and then put a point at the same place on each side of the square, kind of like we're rotating it. And then build another square inside of this. So if you look, what we just did is we built four triangles, and we can call that AB, 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 AB. And since these are all right angles, we can call this C, 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 C. So we have that triangle AB. The triangle has sides A, B, and C. We want to prove that A squared plus B squared equals C squared. Well, if I look at the outside of each side of the triangle, each side has a length of A plus B. Sorry, each side of the square has a length of A plus B. So that means that the area of that square has to be A plus B squared. And then, let's see, that means if I take the square that's inside, that's C squared, plus the four triangles, which are all 1/2 AB base times height, this sentence has to be true, because the area of these four triangles plus the area of this square, so this is the area of the four triangles, plus the area of the square, has to equal the area of the large square. Right, so on the left-hand side here, if I expand this using binomial multiplication, I get a squared plus 2ab plus b squared. And let's see, I got a c squared here. 4 times 1/2 is 2ab. If I subtract 2ab from both sides, lo and behold, I'm left with a squared plus b squared is equal to c squared. So I have proven the Pythagorean theorem. All right, so the Pythagorean theorem is not new. It's something that shouldn't surprise us. Okay, so this theorem has a converse. So we're going to say that there's a converse to the Pythagorean theorem. Okay, so this has 3 parts. Okay, C is the longest side in every triangle. Okay, so we're always going to have C squared, C squared, C squared, C, not A, C squared is always the left side of this equation. And then A squared plus B squared is going to be the right side. Now, we know this. We know that if these are equal, then we have to have a right triangle. If c squared is bigger, then by the hinge theorem, we're making that right angle bigger. So this is actually like a direct corollary of the Pythagorean theorem and the hinge theorem. So that angle has to become obtuse because it's becoming larger than 90. And if c squared is less than, but also by the hinge theorem, it has to be acute, less than 90. So this is our converse. C squared is equal when it's a right triangle. C squared is bigger than when it's an obtuse triangle. C squared is less than when it's an acute triangle. Now, we have 2 special right triangles. We have a 45, 45, 90 right triangle. Typically, when we deal with the 45, 45, 90 right triangle, it's an isosceles right triangle. This is a 45-degree angle. This is a 45-degree angle. This is a 90-degree angle. we would say that this is x, and if we use the Pythagorean theorem, we get that that is going to be x times the square root of 2. If you think about this, x squared plus x squared should equal c squared. 2x squared is equal to c squared. Take the square root of both sides. X times the square root of 2 is c. So that works. Okay, so like a quick example would be if this is a 45, 45, 90 right triangle, if this is 3, this also has to be 3. That side has to be 3 times the square root of 2. Okay, so what if we go the other way? What if we're given a 45, 45, 90 triangle, and we're given this as x? Then what happens is that this becomes x over 2 times the square root of 2. And so does this. So literally, if I had a 45, 45, 90 right triangle, and I'm told that that is 8, then this has to be 8 over 2 times the square root of 2, which makes it 4 radical 2. And since these have to be equal, if that's 4 radical 2, this also has to be 4 radical 2. So you just take that number there, divide it in half, and stick a radical 2 on it, and then you can go from the hypotenuse to the short side of the triangle. The other special right triangle is a 30, 60, 90 right triangle. So in this example, this is like half of an equilateral triangle is what it is. So this side, there's the 90, that's a 60-degree angle, that's a 30-degree angle. The way this triangle works is that if this is x, the long side is 2x, and this is x times the square root of 3. Now I know this is 2x because if this was an equilateral triangle, this would be 60, 60, 60. All 3 sides would be equal. Not too bad there. So this is 2x in length, this is 2x in length, this is a 2x in length, which means this is half of it has to be half of this. Right? So how do we get this x radical 3? Well, we know that x plus something, x squared plus something, has to be 2x squared, right? So x squared plus something has to be 4x squared. Subtract x squared from both sides. The something squared has to be 3x squared. Take the square root of both sides, and we get the square root of 3x, or x radical 3. All right, so let's see some examples of this. So let's say I have a 30, 60, 90, so this is 60, 30, 90 right triangle, and I know that this is 4, right? So that means that this is 8, and this is 4 radical 3. So that's not so bad, right? Take this, double it, get that, and then get the other one. The second way that this problem could set up, let's try not to make that tail. There we go. Oh, too wide. The second way this problem could set up is you could be given this side, right? But that's not making this much harder, right? So if this is the 30, this is the 60, this has to be half of that, and then you just slap a radical 3 on here. So let's say that this is 12. That would make this 6, and would make this side 6 radical 3. So we've dealt with, like, if I'm starting with the short side, just double it to get this and put a radical 3 on it to get that. If I'm starting with the long side, take half of it to get this, and then put a radical 3 on it to get that. What if I'm starting with this side, this medium length side? Let's take a look and see what happens there. So let's say again, I'm starting with a triangle where I know the length of, so this is 60, this is 30, this is 90. I know the length of this side, and I want the other 2. So the trick there is to take that side and divide it by 3 and slap a radical 3 on it. And to go from here to here, you just have to double that, right, to get there. So if this were, let's say, 18. 18 over 3 is 6 radical 3. And then I have to double it, so this is going to give me 12 radical 3. Okay, so we got the Pythagorean theorem. The Pythagorean theorem says if I know two sides of a right triangle, I can find the third. But there's these special cases, the 45, 90 right triangle, which is like half of a square, says that I have an x radical 2. So if I know one of the sides, I know the other two. And if I have a 30, 60, 90 right triangle, then I get x radical 3 and 2x. So if I know one of the sides, I can get the other two. All right, so we're going to do some practice with this in class, but that's the general overview.